cross-bonding cable. This is an example of a three-phase high-voltage cable. The cable screens are grounded at both ends, and that makes a loop and may cause an excessive currents in the screens and losses. We utilize the cross-bonding to reduce the currents and losses in the screens. You can see the electric scheme here on the slide. The total cable length is 21 kilometers. There are two link boxes placed 7 and 14 kilometers away from the start. The cable carries alternating current of about 1.5 kiloamperes, root mean square value. Our task is to calculate the losses in the conductors and in the sheaths. Okay, let's start QuickField now. In QuickField, I create new problem. Cable AC. Next. Problem type is AC magnetics. Frequency is 50 Hz. The cable length is 21 kilometers. Let's change the length units. 21 kilometers. Model class is plane parallel. I'm going to simulate only the cross section, a single cross section of the cable. And I better change the length units back to millimeters. Okay, and I'm going to use the circuit file to specify the connection, the electric connection between the cables. So I need circuit file. Type in the circuit file name here. Circuit 1, finish. On the left you can see the problem pane, and on the right is the geometry model editor window. You can draw the geometry model here, or you can import the geometry model from the AutoCAD DXF file. The model is simple, so I'm going to draw it from scratch. And I'd better take the dimensions from the IAC standard example. Here you can see cable dimensions. So in QuickField, I insert a shape, a circle with the diameter of 57.5. This would represent the conductor. Next, I will insert a circle with a diameter of 59, 105, 106, 114, 122. Zoom to fit. Here you can see the geometry model of the cable. Let's assign labels. Through labels we can distinguish geometric objects and provide material properties. Switch to Select Objects mode, click the object to select, and type in the label name here. This is conductor. This is the dielectric. This is sheath. And this is sewing. And these thin layers are semiconducting material. This is conductor screen. Conductor screen. And this one is core screen. Okay, so now you can click the label in the tree and see the corresponding geometric object. Well, in fact, we have 3 cables, so I better to rename this conductor A, and this would be the sheath A. So There are 3 cables, and the cables are buried at the depth of 1 meter, and the spacing between cable centers is 300 millimeters. So I'm going to select all these, right click, duplicate selection, displacement to the right by 300 millimeters, and again select, right click, duplicate selection, displacement to the left by 300 millimeters. Now zoom to fit. Again, select these cables and move them down by 1 meter. Okay, and here we should draw the ground block and the air block. QuickField cannot simulate the field distribution in the infinitely large space, so I should draw some blocks of finite size. Switch to insert mode, draw the line here. This would be the boundary between the earth and the air. Now change the line type to a half arc and draw the boundaries. This would be the earth, and this would be the air. Switch to select objects mode, click to select and assign label air, earth. And at the boundary, I assign label boundary. Okay, we have label for the conductor A, but we need also labels for the conductor B and C. So this would be A. Click to select. This would be conductor phase B, and this would be the conductor phase C. And the same for sheath. This is the sheath phase B, and this is the sheath phase C. Okay, now let's assign physical properties for the blocks. Double click the label in the tree and provide magnetic properties. For the air, I specify magnetic permeability of 1. And for all insulating blocks, I specify magnetic permeability of 1. For conductor screen, for the core screen, for the serving, and for the earth. For the conductor A, I specify permeability of copper, which is 1, and electrical conductivity of copper, which is 56 megasiemens per meter. Okay, and the same for the conductor phase B and conductor phase C, 56 times 10 to the power of 6. The sheath is made of lead, so the conductivity here is 3.9 megasiemens per meter. Okay. Far away from the cables, the magnetic field fades to 0, so at the boundary, I specify the 0 magnetic potential. Now, we have finished with the geometry model and with the material properties. Now let's edit the circuit file. Double-click the circuit file. In the circuit, you should put all the conducting blocks. These are conductor A, conductor B, conductor C, and the sheath A, sheath B, and the sheath C. And you should use wires to connect the blocks. Sheaths are grounded at both ends. like this. And you might like to add the grounding resistance, say 4 ohms. Conductors are connected in star, and we should add the current source here. Okay. Now that's it. Let's provide the current value. Open the example. The current is 1580 amperes. In fact, this is the root mean square value. And in QuickField, we should specify the magnitude, which is times square root of 2 more. So this is the root mean square value. This is the magnitude. Okay, for the phase B, the same magnitude of the current, but the phase shift is, this is a 3-phase system, 120 degrees. For the phase C, same magnitude, and the phase shift is 240 degrees. Okay. Now everything is ready, and the last step before I can run the analysis is to build the finite element mesh. Just press this button, and the mesh will be generated. Now save all problem files and solve the problem. The problem is solved. Let's take a look at the results. Here you can see the magnetic field lines and the current density distribution. Let's zoom in. Let's check some values. I'm going to use the contour tool, click to select the conductor, open the integrals, and calculate the current. This is the current. Remember, this is the magnitude. If I divide the magnitude by the square root of 2, I should get the root mean square value, which is 1580 amperes, as we have specified. Now let's measure the current in the sheath. Now the sheath is selected, and the current there is, again, this is magnitude, divided by the square root of 2, 762 amperes. And what are the losses? Here it is. This is per 21 kilometers of the conductor length. So let's divide this by 21. That is 94 kilowatts per 1 kilometer of the cable length. An enormous value. Okay, we have simulated a straight cable without the cross bonding. The cross bonding is used to reduce the loss in the sheath. Let's take a look at the setup again. You see, in fact, there are 3 sections, and each section length is 7 kilometers. So what I'm going to do is to place in the same geometry model all 3 sections as independent parts, and then use the electric circuit to interconnect the sections. So I open problem properties and change the model depth to 7 kilometers. Let me check. 7 kilometers. Okay. Yes. Now I open the geometry model, and I need 3 more sections. So I'm going to select all these and drag and drop here, and another section, drag and drop here. And I should assign different labels to be able to distinguish sheaths in different cross sections. So let's go here. This would be the sheath A1. This would be the sheath B1. And this would be the sheath C1. Okay, and here we will have the sheath A2, B2, and C2. And in the last geometric model, we will have the sheaths A3, B3, and C3. I leave the same labels in the conductors because the conductors are not interconnected. Only the sheaths are interconnected. Okay. Now let's provide physical properties for these sheaths. They are the same for all sheaths. 3.9 times 10 to the power of 6. I better copy and paste it here. And for the sheaths C1, C2, and C3. And I do not need this label anymore, so I can remove it. Shift B, Shift A, I remove them. Now, if I run the analysis as is, again I will get the high value of losses. Let's open the electric circuit file and connect these independent geometric models in the circuit. Open the circuit file. I have no more Shift C, Shift B, Shift A. Instead, I have Shift A1, B1, and C1. And if you check the connection scheme, after A1 we have B2 and then C3. Okay. Shift B2 goes here and Shift C3 goes here. After B1 we have C2 and then A3. C2, A3. It is 1, 2, 3, 1, 2, 3, 1, then 2, and then 3. Now that's all. Let's connect them. Again, the sheaths are grounded at the ends, but now they are interconnected. The conductors remains intact. They are not interrupted. So there is no need to assign different labels to the conductors, but we should make sure that the conductors are connected in series. So you should open the label properties and switch to series connection. Because now in the geometry model, there are 3 conductors with label B. Here, here, and here. 3 conductors with label B. and each conductor carries the same current, so they are connected in series. And for the conductor phase C, again, the connection should be in series. Now we should build the final element mesh, save all problem files, and solve the problem. The problem is solved. Let's take a look at the results. Here you can see 3 sections of the cable. And each section length is 7 kilometers. Again, let's measure the current. I zoom in, and now I will click this conductor. Integrals. Total current. If you click another conductor, you will see that you have the same total current. 2234, which is, as you remember, 1580 amperes Rotman square value. Now let's check the current in the sheath. Let's zoom in, click to select the sheath. The current was 1000 ampere, peak value or 765 Rotman square value. Now the current is 32 amperes only. Let's check another sheath. Contour, remove contour, zoom in, contour to click, 34 amperes. And the losses are, remember the losses was 80, remember the losses were 94 kilowatts per 1 kilometer of the cable length, or 94 watts per 1 meter of the cable length. Now the loss is this value, and I should divide this value by the cable length, which is 7 kilometers. Now the losses are 1.8 watts per 1 meter of the cable length. It was 94. Now it is 1.8. Apart from the field picture, you can take a look at the electric circuit results. Here again you can measure the currents in the conductors. This is the Rotman square value. Or you can just hover and see the value. And the current in the sheaths are 24, 22.6, 22.6. So this way you can simulate the cable with the cross bonding. If you search for the cross bonding cable on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the result pictures, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition that you can download from our website for free.